All right, continuing on with logistics in the realm of dealing with population growth. I just want to give you a bit of a introduction, to uh, resulting terms from what we have when performing partial fraction decomposition. And if you have, like, for these three items, and for the stuff we will be encountering regarding population growth, they will sort of run along the lines of taking the reciprocal of the variable of interest times difference uh, involving that variable. Like if you have dx over x times the quantity of x minus m, once you do partial fraction decomposition and attain the antiderivatives, like for this we have negative 1 over m times the natural logarithm of the absolute value of x plus 1 over m times the natural logarithm of the absolute value of x minus m. And if you notice, you have both of these terms have the coefficient in the form of 1 over m, but in the case of the first term, it is a negative. And going back to the sum indifference properties of logarithms, again, if you were to translate what we have in terms of what is present in addition and subtraction and rewriting in terms of multiplication and division, you will recall that any attachment that's associated with a positive logarithmic term is going to be in the top part of the fraction, and anything that stems from a negative logarithmic term in the same base, it is going to go to the denominator. So in this case, we have x minus m is at the top and x is on the bottom. And notice we have, with switching the order of m and x, notice that we have the natural logarithm of x has alongside it a positive coefficient of 1 over m, and the reordering of x minus m to m minus x, we have the resulting antiderivative to have a negative 1 over m for the coefficient, and this time x is at the top, and the binomial we have, because it is attached to a negative natural logarithmic term, that is going to go on the bottom, and we have 1 over m for the coefficient. And anyway, for any positive antiderivatives in a natural logarithm, the attachment goes at the top. Anything that stems from a negative, that particular attachment goes on the bottom. And for what we have regarding logistic growth, and this is like looking at projected population amount, let's say years from now. And for what we have with bounded populations and logistic growth. Now, bounded, you're looking at reaching a saturation point. And now, and we have, for this form, we have population P, where we have the change in population with respect to the change in time, is equal to a proportional constant K times the population times the quantity of M minus P, where we have M to be the maximum attainable population. And let's say that just in the case of expressing what we have in terms of P. All right, so if I were to separate the terms or expressions in P, so you got dP all over P times the quantity of M minus P is equal to K dt, and if I separate, I can integrate, and notice we have NP instead of x. Notice you have like dx over x times the quantity of m minus x. And if you notice, you will have the reciprocal of m, and in this particular case, you're going to have p, and we have x at the top and m minus x at the bottom. And for what we're going to have here, so we have 1 over p times the natural logarithm of what is going to be p all over m minus p and that is going to be equal to kt plus c. And if I were to multiply by p, just get the natural logarithmic term by itself. So we have the natural logarithm the absolute value of the ratio of P over M minus P. You have K times P times T. Then we have P times C, and by then you can just write that as alpha, whereupon we have alpha is equal to P times C. And if I look at raising, what I have here, that is treating both sides as powers, to which we're going to have the natural logarithmic exponential base e to be raised. Okay, so I have e to the kpt plus alpha. And if you notice in the follow through, okay, so we have e to the kpt times e to the alpha, and a constant raised to a constant. Okay, that's going to be yet another constant, so we'll just call this beta. So we say we have beta times e to the kpt, right? And again, from what we have on the left hand side, okay, we're going to have resulting, and I could theoretically say plus or minus P over M minus P, but the positive and negative is going to be absorbed into the constant. And so for what we have in this particular case, right, so this is what we're going to have in terms of the ratio. And now if I multiply both sides by M minus P, okay, so if I multiply by the quantity of M minus P, so left hand side, okay, so that's going to be at P. Then we have beta times the quantity of M minus P times E to the kpt. And looking at distributing, so you have P is equal to beta M times E to the kpt minus the constant beta times P raised to the E, I should say times E raised to the kpt. Right. And notice we have indirect fashion. Okay, we have a couple of P terms, and if I join the P terms together, so I have just the letter P by itself on the left, and if I join with beta times P times E raised to the kpt and if you notice the case, so we got, so if I add these terms together, and I would just go ahead and write solely in terms of P. So we have P times the quantity of 1 plus beta times E to the kpt is equal to beta times M times E to the kpt, and getting P by itself. Okay, so you have beta times M times E to the kpt all over 1 plus beta times E to the KPT. And like in the notation that some authors like to use, okay, they like to keep it to just one exponential term, but this is one way that you can express this. And another way is to say that if I multiply all the terms out by e to the negative kpt, that is, multiply the ratio that we have here by e to the negative kpt. So we have beta times m all over e to the negative kpt plus beta. Okay, and that is another way that you can represent the population in theoretical terms. And we'll be looking at an application shortly.